A couple of quick definitions that weren't mentioned in class, except that they were mentioned, at least this one was mentioned, this one wasn't. Okay, R of A is the range or column space of the matrix A, and we see that here, and we'll explain this in a minute. This symbol, this Greek letter applied to A, means the row space of A. Now, I chose this Greek symbol not for its name, but because it isn't used a whole lot in the context of linear algebra that we're working with right now. But it happens to be the Greek letter rho. So rho of A is the row space of A. That's kind of a pun. Okay, but that kind of makes it easy to remember. Okay, so we have the picture of vector space V, vector space W, and a matrix A that maps elements of V to elements of W. Now we can consider A to be a real valued matrix, okay? And V to be, okay, well, let's say A is M by N, then V would be Rn, and W would be Rm, because an M by N matrix acts on vectors of length M and gives you vectors of length M. Okay. Then we have the familiar, I hope the familiar breakdown of V into the row space of A and the null space of A, the perpendicular or orthogonal subspaces. Now, we can also say that the whole space V is a direct sum of these subspaces, these orthogonal subspaces, so that if V is any vector in V, it has to be the unique sum of some vector in the row space and some vector in the null space. And sometimes we would call these vectors, I could call this vector V sub rho, and this vector V sub n, so that V is equal to the unique sum V rho plus Vn. Now, more about unique sums and so forth. This simply means that there's only one vector that you can use from the row space, and only one vector you can use from the null space in order to get the vector V. And that's true for any vector in the whole space. And in that case, we say that the space is the direct sum. So we could say that V is the space rho of A, direct sum with n of A. And this is exactly what this means. Okay, over here in W, well, we have R of A, which we say is the range or column space. So this equals column space. Okay, well, we have the C. This is a column space of the matrix A, which is R of A, the range of A, the set of all vectors you get when you map all the vectors from A using this transformation, the transformation T of V equals AV. Okay, so the column space is the row space, is the range of A, see I'm wanting to call it row, range space of A. And this is, it turns out, very easy to see that this is the row space of A transpose. And we can write that with the Greek symbol rho applied to A transpose, because this is the symbol that gives us the row space. Now, to see that the column space of A is the row space of A transpose is very straightforward, because A transpose is what you get from the matrix A if you just switch the rows and the columns. Follows immediately that the rows of A, the columns of A span exactly the same vectors that the rows of A transpose do, because the rows of A transpose are exactly the same as the columns of A. Okay? Now, for any vector space and any matrix that acts on that vector space, we can break the vector space into its row space, and of course this is now the row space of A transpose, and into the null space of that matrix. So the null space of this matrix A transpose is orthogonal to the row space. And again, we have the characteristic that any vector W in this space is a unique sum of W row and some Wn, W row in the row space of A transpose, Wn in the column, in the null space of A transpose. So that W is uniquely equal, and I write that as an equal with an exclamation point over it, uniquely equal to W row plus Wn. Okay, again, a unique sum in that there's only, for this W, for any W here, there is exactly one vector here that can be added to exactly one vector here to give you this. There is no other vector here that could be added to any vector from here, and there's no other vector here that could be added to a vector from here to give you this particular W. Okay, that's some background, and now what we want to do is we want to move toward using this picture to do the best fit straight line to the data that we get in our depth versus time model. Now we know that we can, let's say we have 5 data points in the depth versus time model, okay? We know we can select 3 of them and fit a quadratic to it. And we get these equations, and we should understand completely where these equations come from that give us this matrix equation. And this matrix has to be invertible, unless we have 2 different t-values with different, unless we have the same t-value with 2 different y-values. This matrix will be invertible, and that can be easily proven. Which means that we can find the exact numbers A, B, and C to put into our quadratic model being y equals at squared plus bt plus c. That for these 3 points will give us these values of y when we plug in these values of t. Now that's only for these 3 points. It doesn't work for these 2 points. It might, but if this is real world data, it's unlikely that it would. And you know, it's very possible that your y versus t isn't perfectly modeled by a quadratic function. You're not going to see that just by taking 3 points, because 3 points, you'll always get a perfect quadratic model. Because this matrix is invertible, so you can always get the A, B, and C values that yield these y values for the corresponding t values. So we want to look at what you do if you want to use all 5 data points.